It's right there, r, and then r. Does that make sense distance-wise? Understand? It just tells us how the radius of our interval. It tells us nothing. The capital R tells us nothing about the endpoints. It just tells us about, kind of the width of the interval. Make sense? So if you're asked on a problem to find the radius of convergence, do you have to test endpoints? We got to that point without testing endpoints, didn't we? Algebraically, we can turn that into that without doing any testing of endpoints. If you're asked for radius of convergence, it's an easier problem because you don't have to test endpoints. If you're asked for the next thing, which is called the interval of convergence, then you must test the endpoints. And the interval of convergence is going to be in one of 4 different things. You're either going to have an interval include both endpoints, you're going to have not include both endpoints, include the left, not the right, or include the don't include the left, include the right. There's only those possibilities. Yeah? So, can you all see how a problem like this could be a nice problem for giving all Cal 2 students? You have, the question would be, find the interval of convergence. And that's it. That's all it would say. So the student needs to know they're going to have to run some sort of ratio test. That's going to test, make sure they understand how to do simplifications of things. They're going to have to take a limit at some point, so L'Hopital might be involved. They're going to get a result. If it's an interval, they're going to have to go check the endpoints, which means they're going to have 2 separate series problems to do. That's a lot, right? That's a lot encompassing one problem.
Are you going to part that out like you did on the previous test where there's A through F?
No, I think that would just be find the interval of convergence. That's it. That's the way it is in the homework. Just find the interval of convergence. Yes? Yeah, I'll post these later. Yeah.
That'd be awesome.
Yeah. Later meaning after the semester. No, I'm just kidding. I'm just kidding. Well, later, I mean, I wasn't specific, right?
I mean, yeah.
But I'm not done with them. I still want to do a little bit more with them. So, but I can put them out. All right, so you ready? Another example. Find interval of convergence sum. I just need to throw that away. Just leave it. Just let it be dead. Okay. Interval of convergence of sum n equals 0 to infinity of -5 to the n x to the n over square root of n plus 1. We're going to go get those sticks. Let's go get those sticks. Throw all these away.
You have to put a square root in there? Come on, man. Talk about this.
Martin, your first one here. Okay, what's the first step, Martin? Ratio test, okay. So will you tell me what to write? Mm-hmm.
Then we're going to start with the fraction of it with n plus 1. So we're going to have -5 to the n plus 1.
-5 to the n plus 1.
Times n to the n plus 1.
I'm sorry?
Times x to the n plus 1.
Okay, sorry, I didn't hit it. X to the n plus 1.
Over the square root of n to the n plus 1 or n plus 2.
N plus 2. Let's just do that.
And then
Okay. Keep going.
times the reciprocal of that, the original, which is just going to be the square root of n plus 1
Okay.
divided by -5 to the n times x to the n.
Okay. All right. Now, so these are all kind of turning out to be the same sort of game that you're playing here, right? It's messing with exponents. So keep going, Martin. What do you want me to do now?
So we can separate out the numerator of the left fraction, both of those into their respective parts with n itself to the power of 1.
Okay, so like -5 to the n, and then times -5 So that's that. And then this one,
X to the end.
x to the n times x.
Which will cancel out with the bottom right.
Okay, that's going to cancel with the bottom right. This one, and then this one, and that one. Good? Okay, good job. All right, let's see who's next. See, Jordan? You good? Okay, so what do you want me to do next?
You can rewrite the limit
Okay, rewrite the limit.
as absolute value
Okay,
of n plus 1 over n plus 2, and you do the root over.
all the root over the whole thing? Okay, so n plus 1. So you want to go ahead and put those together. That's fine.
And then off to the side
Times
times negative 5x.
negative 5x.
And then
Absolute value. What do y'all think? That look good? I like that. I like that.
and then
Okay, so now take the limit, and what do we get? So you do the limit, and you can go in the root, right? And you do that thing, and what do you get there? Okay, so L'Hopital 1. So you don't have to show that on the test. Like your Cal 2, you know, we should just know that that limit's 1 now. And so this is just absolute value of negative 5x, right? No more limit, right? And what should I write next to that now? Less than 1. So this is what I'm saying, or this is what we're saying. We want to make sure that that's less than 1, right? Okay, if we were asked for the radius of convergence, we would almost be done, okay? We would almost be done, because all we would have to do is pull the 5 out, and when I pull it out of the absolute value, it's just 5 because you take the absolute value of it, and then divide, and you get x less than 1/5, right? And so the radius of convergence would be what? 1/5. If that's what was being asked, right? That's not what's being asked, but that's how we would be done at that point. But because we're asked for the interval of convergence, what do we have to do instead? We have to take this and we have to convert it. So how do we convert that over? So you do like negative. Let's do it this way. I guess the question is, how do you want to deal with that negative in there? Or is it going to matter?
It's not gonna matter.
So what should my next line be?
It'll just be 5 times square root of that. Oh, sorry.
So I'm working with this line here.
5, absolute value of 5x less than 1.
So this is a little tricky. Let's do that. Okay, let's pull the 5 out. All right, and then let's divide by 5. So it's the same work we did right here. But now this is the one we're going to turn into the inequality thing, where we drop the inequality, we rewrite it, and we say, what? Less than this, and then greater than negative 1/5. Okay? Just like that. All right, is that our answer? No, that's part of our answer, right? Everything in there, we converge. But we need to check our 2 endpoints, right? So now we check the 2 endpoints. So the endpoint, let's let x be negative 1/5 first. And I've erased the original series, so I'll have to rewrite it in there. It was sum n equals 0 to infinity, negative 5 to the n, x to the n, right? Over square root of n plus 1. Okay, so the question is, does this converge or diverge? And let's see here. Stephen. So Stephen, take a look at that numerator. Just look at the numerator. Something in the numerator is going to clean up.
Yeah, they're going to kind of come together.
Yeah, you can put these together because they're the same powers. And when you do that, negative 5 and negative 1/5 become positive 1. And then 1 to any power is just 1, right? So this just becomes sum n equals 0 to infinity of 1 over the square root of n plus 1. Okay, yes?
N equals 0 or 1?
0.
0? Question was 1.
Pardon? Was it 1 on the original one? No? It's all right. I mean, 1, so if you start a sum at n equals 0 or 1, you're only talking about one term difference, right? So convergence and divergence can never be determined by a single term. Okay. We'll move on, and I think it was Erica. It was, but you fell. You fell back into the, so you might get called again. No, there you are. No, you got cold. Okay, so yeah, what now? Like, so we're looking at this, and we're trying to figure out if it converges or diverges. So any ideas?
Maybe like a p series if we change the square root to a 1/2.
So it looks like a p-series?
Kind of.
Yeah, so you can compare it to a p-series?
Oh, yeah.
Yes? So you want to compare this to a p-series. All right, so when you compare to a p-series, okay, so let's do that. We're going to do compare, or Erica's going to do compare, to a p-series. Which p-series am I comparing it to? You said 1/2?
And 1 over n to the 1/2.
1 over n to the half. So p here would be a half, and what does that do?
It's less than 1 and
If it's less than 1, it diverges. So this is divergent. So you're comparing it to a divergent. Now, you remember with the comparison test, everyone? You had like part I, 2I, 3, 1, 2, part 1, 2, 3, right? Part 1 and 2 was you used inequalities, but part 3 was the limit comparison. So what would you like to do?
I'll do the part 2.
You're going to try and do an inequality? Okay. No, that's fine. Let's go for it. That's fine. But what's the inequality we have to show? This right here is a sub n, okay? And this right here is b sub n. So you want to show what?
A sub n is greater than.
Perfect. Greater than strictly or bigger, it doesn't matter. Okay, this is good. Why is she showing this inequality, not the other way around? Because this diverges, so you want to try and show that the other one always stays bigger than it, right? And then it would also diverge. Okay, so let's put that down here. 1 over the square root of n plus 1 greater than or equal to 1 over square root of n, right? So comparing that to this, and what do y'all think? That didn't work, did it? Okay, Erica, so you're taking the final, you're starting to freak out a little bit. So maybe you try something else? Don't give up on comparison yet.
Like the limit?
The limit one. Let's try the limit comparison. Okay, so this fails. Does everyone agree that failed? Test fails, that means we have to try something else. So let's do the limit comparison test. The limit comparison test, we're using the same comparison, right? Same one. So we need to take the limit as n goes to infinity of, I forget which one they do, a sub n over b sub n? Yeah. So we want to do 1 over the square root of n plus 1 over 1 over the square root of n. Right, Erica?
Yes.
Okay, now, is that going to work? Let's clean it up, right? So I can flip, and then I can wind up putting them all under one root. I can do that, right? And what's that limit, Erica? Okay, so then we do L'Hopital, and then 1. Okay, so what is the result of the limit comparison test say here? If you do this limit and you get an answer C, right? And C is a real positive number, then both series do the same thing. So this worked, didn't it? So this means that, hold on. Max isn't here. Chris. Yeah. So what does this mean? What's our final conclusion? That's right. Since this one, the thing we compared to diverged, it means that this one diverges. I'm sorry, this one diverges, which means
Negative 1 fifth ever. At negative 1 to, okay.
diverges, which means this number is or is not in our answer, is not in our answer. So our interval so far, right? So this means divergence. So this thing right here diverges. So our interval, we are looking at this, we don't want that in our answer, right? We don't want that. Thank you. Okay, now we need to do the same thing, right? But now we need to let x be the other endpoint, which was 1/5. So let x be 1/5. These are actually really fun, aren't they?
Yeah.
Yeah. All right, David? What do we get on this one, David? So it's different than this one for sure, right?
Yes.
Okay, so what does the numerator turn into?
It should be a negative number.
-1, right? Put those two together now.
Negative 1 over.
-1 to the n. Hold on, to the n, right? This time it matters because, yeah, when it was 1, it didn't matter. N doesn't matter anymore because 1 to any power. But that is going to alternate over.
Square root of n.
Okay, and how do you want to handle that, David?
Alternating.
Alternating series test. This is an alternating series, so we can just use the alternating series test. So you have to show that the limit of the positive part goes to 0, and you have to show it's descending, which both would be true. First thing, take the limit as n goes to infinity of 1 over square root of n plus 1. Goes 0, check. And then the second part would be to show that a sub n is bigger than a sub n plus 1, which is the same as showing that 1 over square root of n plus 1 is bigger than 1 over the square root of n plus 2. And that's true because this denominator is bigger than that one. So that checks. So what does it do? Converges. And so do we want to include 1/5 in our answer?
Yes,
This time we do. So we're ready for our final answer. The interval of convergence is the interval -1/5 to 1/5. There we go. Yes?
So the negative sign doesn't matter?
Remember in the alternating series test, you separate the alternating part from the sequence you're checking. Where's your formula sheet?
It doesn't show like.
Yeah, so you see a sub n, it's -1 to the n, a sub n. The a sub n is the thing you're checking. So there's no reference to the -1 to the n in that part. All right. Well, that's pretty much it. Now you get to try. Bless you. But we still have 20 minutes, so we are moving on to 8.6. There's absolutely no way that the final exam would not have a problem like that in it. Okay, so guaranteed you're going to have one. All right, 8.6. Representing functions as power series. So we've been looking at, power series and, this idea of when do they converge, when do they not. But now we get to the whole idea of, like when I gave you cosine x, how do we turn cosine x into its power series, right? We're not quite ready for that yet. But what we are ready for is looking at one particular kind of unique example. So take a look at this series. Okay, what is that written out, that power series? This was a special one. What does this one look like? 1 plus
X plus 1.
plus forever, right? This is a very special power series. It looks, this is probably the first one I ever gave you. And I said it's a very special one because what's happening is you have ones in front of all these things. So the constants in the front aren't changing, there's always one. And we said that looks like a geometric series. I said, this looks a lot like a to the r, ar to the n, ar to the n, where a is 1 and r is actually x. Look in your notes. We've already talked about this one. Okay. Now, does this power series converge? It does when the absolute value of x is less than 1. Okay, so this does converge when the absolute value of x is less than 1, right? And what does it converge to? What is it equal to? A over 1 minus r, so 1 over 1 minus x, if the absolute value of x is less than 1. This is a geometric series with the a being 1 and the r actually being x. And if we look at this geometric series will converge to a over 1 minus r so long as the absolute value of r is less than 1. That's basically everything about geometric but rewritten in terms of x. Are y'all good with that? Okay, now, here's what we're going to do now. Just remember that, we need that, all right? I would like us to, as an example, express f of x equals 1 over 1 minus, or let's say plus 5x as a power series. So you see that function? That looks like a rational function from college algebra, right? I'd like for us to express that as a power series. So somehow, and I hope this has not gotten lost in everything we're doing. The big idea, big idea is that if somebody gives you a function, it has a power series. In fact, there's a theorem, it's one of the theorems that always is in my mind from graduate school. It's called I can't pronounce it, but it's called the Weierstrass approximation theorem. Basically, it says given any continuous function, you can always approximate it with a power series as good as you ever need to. So if this is a function, right, we should be able to approximate it with a power series. So can we do that? Well, pardon, what?
You can do the ratio.
No, this is not a series. This is just a function. Okay, I want to create the series that gives you that function. That is the same as that function, like the cosine, right? And we have the series that went with it. I'm trying to start with this and come up with the power series. So let's look at this. We have this thing. That's what I just had on the board, right? If we ever see 1 over 1 minus x, that's equivalent to this infinite series. so long as what? The absolute value of x is less than 1, right? So this right here, if I rewrite this, let's try and make it look like this. Do y'all see that? See how that looks like this is 1 over 1 minus 5x? And you see that kind of fits into this format? And y'all see like x for us here is really kind of a dummy variable. So for us over here, it's this whole thing, right? Isn't it? So this should be equal to the sum is n equals 0 to infinity of what? Negative 5x raised to the n. So long as what? The absolute value of negative 5x must be less than 1. So this is only going to work. This thing will only be the same. This will only be the same as this if the absolute value of negative 5x is less than 1. And that is the same as saying the absolute value of x is less than 1/5. Okay? Now, this is a power series. I'm going to rewrite it. Try and get it in like the standard form. So I'm trying to make it look like this. I'm trying to make that power series look like sum n equals 0 to infinity c sub n x minus a to the n. That's your general form of a power series, right? So I've created the c sub n. What's the c sub n for us? That thing, right? And then this right here is that. So this is a power series centered where? At 0. Because I have x to the n, right? So that means the a is 0. Okay? No? Yes? No? Yes?
So you're allowed to have an n in your c sub n term?
Absolutely, because this constant is a function of n. As n changes, that constant changes. So this c sub n implies that it's a function of n. Okay? So if I were to somehow graph this power series on the same axis as this function, they will be identical functions if you're looking in this interval. Okay? I believe I have a picture. I have one close to it, no. Here we go. Here's one. It's not the exact same function. Is that all right with you? But it's still the same idea. I just changed, like I put like a 4 up here and it's slightly different. So do you see the red function? Do y'all see the red one? Okay. I'm trying to zoom out here a little bit. Okay, it's a rational function. It's a red one. And ignore the vertical line here. That's just my computer freaking out. I'm approximating right now with a line, which is not a very good representation. But I'm going to start adding more to it. So there, now it's a linear. There's quadratic. So it got better to this, didn't it? Like got closer to the red one. And now I'm going to keep going. Just watch what happens. I think I've slowed my computer down too much here. So would you agree that the black one is a really good approximation over here? Like in here, like we're dead on, like we are doing great. But as soon as I get out here, it's like, wow, it just does not work well, right? And over here, so it looks like this series is only good on this little interval. And that's why we had to have the absolute value of that thing, right? We had on our problem the absolute value of x had to be less than 1/5. So we had to be within a certain little window. This works. Okay? So if I was interested in what's happening over here, how would I change it? I would change A. I would change A in the problem. Remember, the x, that's where you're centered at. So if I change A, I'm going to say, look, I have a great approximation within this little window, and if I change A, I'm going to just slide that window over here, and now my approximation will be good there. All right? That's the drawback to where you have an interval of convergence, is that you can't trust it everywhere. You just have to move it around. But okay, I just wanted you to see like a visual of what's happening there. 9 minutes. Let's try another one. So express this one as a power series. F of x equals x to the 5th over 2 plus 3x. This will be our last one of the day. All right, right now, the only way we can turn a function into a power series is using this right here. That's all we have. Right? That's it. I've not shown you anything else but this, right? So somehow we have to use this to convert that to a power series. So one thing I could do is I could pull the x to the 5th out. Not pull it out, but just write it on the side. And then over here I could write this. Right? Now in this formula, I have a 1 here, don't I? I have a 1 here. So I need a 1 there also. So let's pull a 2 out of the bottom. Now when I pull that 2 out, what happens to this other part? It becomes 1 plus 3/2 x. Okay, getting closer. I'm going to write that as 1/2 x to the 5th times 1 over 1. So I brought the 2 that's down here. I just brought it as a 1/2 out in front of the whole thing. And then what do I have down there? 1 minus negative 3/2 x. Again, needing a minus here to match the formula, I need to make that a minus minus. Do you all agree with that? Okay, now, this should be equal to 1/2 x to the 5th times this thing will turn into this, right? Sum n equals 0 to infinity of what to the n? Negative 3/2 x to the n. And this is valid, right? This is valid so long as what? The absolute value of 3/2 x is less than 1. Which is the same as saying the absolute value of x is less than 2/3. You could pull the 3/2 out and then multiply by the reciprocal and you get this.
Do you take either one?
Do this, yeah. But you need to state it. Because we're not saying that these are equivalent all the time. It's only equivalent whenever this is true. Okay, now, does this look like a power series? Does that look like the general form of a power series? Does it look like sum n equals 0 to infinity of c sub n x minus a to the n? Does it look like that to you? No, it does not, because you have this stuff out here, right? So I'm going to push that in. So this is going to become sum n equals 0 to infinity. Put that inside. I'm going to get 1/2 x to the 5th times negative 3/2 to the n times x to the n. So I just applied the n to both of those. Right? And go a little further because this and this, right, are both same base. So I can rewrite that as sum n equals 0 to infinity of 1/2 times -3 halves to the n, x to the what? N plus 5.
Where did this x to the n come from originally? Right here? Sorry.
This one?
Yep.
From here. And on both.
I see what you did there.
Now, does this look like this? Do we have something out front, a number that's going to keep changing as n changes? That's our c sub n, right? That's our c sub n? Agreed? Okay. Do we have x minus a to the n? Yes and no. It's yes because we have x to a power, right? But it's n plus 5 instead of n, right? So we want to be able to be comfortable at this point to leave it like this, where n is going to stay here, start at 0, and then we have n plus 5 here, or we need to have the ability to switch this to n instead of n plus 5. And you'll see as we move on why this is important, all right? This is, I know we're in the last 4 minutes here, but this is a very important last technique. Right now, I would like to rewrite this so that this is n and not n plus 5, all right? So it'll match the formula, match this up here. So watch what I'm going to do. What am I trying to do? I'm trying to make n plus 5 turn into an n. That's what I'm trying to do. Make an n 5. So how could I do that?
Just subtract 5 from all the ends.
Subtract 5 from all the ends. So that's, in other words, you're saying subtract 5. I'm going to write it this way. Everywhere I see an n, I'm going to replace it with n minus 5. All right? Now, why is this going to work? If this n was n minus 5, then it would be n minus 5 plus 5, which would be n, wouldn't it? I'm going to replace that. But I have to do it everywhere. Everywhere. Okay? So watch. I'm going to write the sum. Sum. N minus 5 equals 0 to infinity. 1/2 to the -3 halves to the n minus 5, then x to the n minus 5 plus 5. So do y'all agree I've replaced all my n's with n minus 5s? Now let's see what happens here. What's another way you could write this, that n minus 5 equals 0? N equals 5, just add 5 to both sides of that equation. So sum n equals 5 to infinity. Now this is a bit messy, but I can just leave it because the formula here just says it has to be c sub n. It doesn't say what my power has to be. So I'm just going to leave that as, well, I didn't need that. I didn't need that. -1/2, 3 halves to the n minus 5. And then this right here is now x to the n. So now this is my c sub n. This is my x minus a to the n. Now I agree, our series is not starting at 0 anymore. So power series technically start at 0, but power series also have an n as the power. And the reason why we have to be able to do this, all right, the reason why is because as we move into next class and next week, we're going to start differentiating and integrating these things. And when you do that, things on your indexes start to change. And when you try and combine functions together, you need to either get them to all start at the same place or you need them to all have the same power. So you have to be able to switch back and forth. So we'll get more practice with this. I just want you to see first time how you can switch it, all right? Okay, so for homework, you should make sure you take care of everything in 8.5, right? 8.5 is the power series. We just started 8.6, so I wouldn't get too much into that. And we only have 2 more sections out of chapter 8. Yeah, and we only have 3 more classes? Yeah. We're going to be lucky if we get much of chapter 9 in at all. But